So I'll be giving a brief overview of some of the decision support tools or forecasting and decision support tool objectives that we have here at CW3E and how they apply to their research to applications focus within CW3E. I'll discuss some of our multi-model deterministic forecast tools, as well as some of the tools we have associated with the atmospheric river scale. And then I'll pass it over to Jay to go over some of our ensemble forecast tools. Next slide, Jay. So one of the main focuses of CW3E is really bridging the gap between education and research to applications. So this is mainly achieved through science and innovation to try to improve forecasts and observations, demonstrate these improvements, and then provide forecast products in an accessible manner to a wide range of audiences. So this really increases our resilience in both our current and future climates. Next slide, Jay. So the objectives surrounding the CW3E forecast tools that we have here are listed. Our first one is really focused on enhancing the situational awareness of landfalling atmospheric rivers with a specific look into providing uncertainty within the intensity, timing, and duration of these ARs. We also have watershed forecast focused tools that are aimed to aid in the decision support of water resources and FIRO. We'll hear a little bit more about these watershed tools in the next session. To convey confidence and uncertainty in our forecasts, we use multi-model approach as well as ensemble forecasts. We've developed an in-house high-resolution model known as the West Wharf. You'll hear more about this in the next session as well. And then lastly, CW3E produces what we call outlooks or updates when there's an atmospheric river in the forecast, or a summary after they've made landfall. This is where we bring together multiple different forecast products and tools and add our own interpretation and put them all in one place in a news style post on our website. Next slide, Jane. So here's a brief overview of some of the multi-model deterministic forecast tools that we have here. When I say multi-model, this is inclusive of using the GFS, or the Global Forecast System. This is the American global model from NOAA. The ECMWF is the European global model. This is sort of widely recognized. The GFS and the ECMWF are widely recognized as the two best global models out there. ECMWF tends to be accepted as a little bit better than GFS, but not in all cases. We also have products for the North American model, or NAM. This is a higher resolution, more of a shorter term forecast, also provided by NOAA. And then we have the in-house West Wharf high resolution model as well. So we produce quite a few different variables, some focused on atmospheric rivers and some more on general meteorology. These are displayed in a couple of different ways, either in the types of different maps or time series. We also have some cross sections and a few different ways that we show these different deterministic models. Next slide, Jay. So some of the more sort of basic looking forecasts, more of the general forecast maps that you might be used to seeing are shown here. These first ones that I'm highlighting are focused on atmospheric rivers. So the image on the right is showing a forecast of integrated vapor transport, or IVT. IVT is a combination of winds and moisture throughout the atmosphere. This is really the most common variable used when diagnosing or forecasting atmospheric rivers. So this is a variable that you'll see in quite a few of our different forecast products. We also have different tools looking at just integrated water vapor. So instead of winds and moisture, this is just looking at winds, or just looking at moisture, excuse me, and then quite a few different products looking at precipitation. And all of these are available from several different models. This is at the top there, most of which go out to about 7 days, some a little bit shorter depending on the model. Next slide, Jay. And we also have several different tools focused more on general meteorology variables, things like winds, heights, temperatures, vorticities at several different levels throughout the atmosphere. We also have some plans to add some new additional variables over the coming months. Next slide, Jay. So another tool that I'd like to highlight is our time height mediagrams that we produce out of several different models. These are really useful for a point-based or a location-specific forecast. So in that map in the center there, you see all of those different dots. So you can choose one of those dots, perhaps the area of interest that you're interested in, and you can get a point-based forecast for that location, either for the next 3 days or the next 7 days. So the top panel of this image on the right here, the shading there is representing the water vapor flux, or there's also options showing the relative humidity. So this top panel is a time height cross section. So we have our forecast time on the x-axis and then our height or pressure on the y-axis. So being able to look at this this shows us the vertical distribution of the moisture within the atmosphere. So this gives us a good insight of how an atmospheric river might interact with terrain. So this gives us an idea of either the inland penetration of an atmospheric river, as well as the potential orographic enhancement of precipitation within the AR. So also shown on that top panel are the winds throughout the atmosphere, as well as the freezing level or 0 degree C isotherm shown by the black line. The middle panel is focused more on precipitation. We've got bar graphs for 3-hour precipitation at this location, as well as a line showing the height of the 0 degree C isotherm. And then the bottom panel there is showing the atmospheric river conditions, the time series of IVT in the red line and IWV in the blue line, with the air conditions shaded within gray. Next slide, Jay. So the next slide here is just to highlight some slight changes that you may see if you pick a location that has some higher terrain. At the top section there, you'll see the gray bars sort of covering up the bottom of that figure that's showing that this area is underground, or basically the surface height is at the top of that gray bar there. And then in the middle, this is just to highlight that when the dashed line that's going across there is showing the surface height of this location, and then the precipitation bars, as well as the height of the 0 degree isotherm, will change color based on how that 0 degree isotherm is in relation to the surface height. So if the freezing level is below ground, we would expect freezing precipitation, so the bars and the line turn blue. And in the opposite of that, if it's above ground, we expect liquid precipitation. You see green bars and lines there. Next slide, Jay. So the next section here will be focused on the atmospheric river scale. Again, we use a multi-model approach for this, using just the GFS and the ECMWF here, both deterministic as well as some Ensemble products here. The main goal of the atmospheric river scale is really to enhance that situational awareness of landfalling atmospheric rivers, and also give an input into the benefit versus hazard spectrum of the ARs. Next slide, Jay. So the AR scale combines atmospheric river intensity as well as duration to really convey that benefit hazard spectrum. The scale, ARs are mapped out on a 1 through 5 scale, as you can see on the bottom middle of this slide. ARs 1s and 2s are more primarily beneficial, whereas the stronger ARs, the 4s and the 5s, are more primarily hazardous. Go ahead, Jay. So this scale is derived for a specific location. So in contrast to some other scales out there, like a hurricane scale, a given AR is not given a ranking for the entire storm. It is fully location dependent. So in the strongest part of an atmospheric river, it may be an AR5. However, on the outsides of the in locations that are not experiencing as strong AR conditions, it may be lower on the scale of a 1 or a 2. So in terms of how you would determine the atmospheric river scale, you would pick the location of interest. You determine your atmospheric river duration by defining the continuous period of IVT over 250 units. You then determine your atmospheric river intensity. This would be the maximum IVT during that AR. And then you use the AR intensity and duration and map that onto the AR scale matrix that you see in the middle there, with the duration on the x-axis and the intensity on the y-axis, and that would give you your scale rank. Go ahead, Jay. And this scale can also be mapped out here. This is a nice way of seeing the location dependency of the AR scale. In this example, there's locations in the core or the strongest part of the AR where it was an AR5, and then locations on the northern and southern edges that were lower on the scale all the way down to 1. Next slide, Jay. So the few of the forecast tools that we have available for the atmospheric river scale, the map on the left is showing the maximum forecasted AR scale over the next 7 days at these coastal locations. Each one of those dots are color shaded based on the AR scale from 0 to 5. If you're interested in one of those locations, you can choose that on the map and you would see an image similar to what's in the middle here. This is a time series of IVT set up sort of similar to a river hydrograph, where the left side is the observations or the previous 7 days of IVT. And then the right side is showing the forecast for future 7 days of IVT in an ensemble framework. And Jay will go over a little bit more on how this plume diagram on the right works in a few minutes. So I'm just going to focus on the AR scale portion of this. So the color shading, both on the left and the right side there, are representing times of an atmospheric river at this location. The color shading is based on the AR scale, again, 1 through 5. And then go ahead, Jay, click one more time. And then you can see how these different ARs map out onto the AR matrix. So for example, the AR in the forecast period time here in the red has a maximum IVT forecasted of 1,000 units with a duration of 54 hours, represented by the B in the diagram there, showing as an AR5. Next slide, Jay. Oh, as well, and you can sign up for atmospheric river scale alerts for anyone who's not aware on our website there. You can select whatever region you have of interest, as well as how often you would like to get them, either through text message or email, right there on our website. Next slide, Jay. So I mentioned earlier, the AR scale was really focused on trying to display the benefit hazard spectrum. And one way we can look at how well it's doing at that is to relate atmospheric rivers to National Weather Service's watches, warnings, and advisories. So Jay Cordeira and one of his graduate students, Sam Bartlett, recently released a study here, basically doing that, looking at trying to correlate the atmospheric river scale with National Weather Service watches and warnings. And what it showed here is illustrated on the map on the left that a large majority of watches, warning, and advisories over the West Coast were associated with landfalling ARs, especially throughout California and the Pacific Northwest, where it was over 75% of them. While not all ARs do produce hazardous weather, higher events on the AR scale were much more likely to necessitate a watch or a warning. This is also shown on the bottom right here panel, on the bottom right figure here as well, showing an exponential increase in the potential for hazardous weather, as well as watches, warning, advisories, as you increase on the scale here. So another important key to think about here with the AR scale is that the antecedent conditions play a significant role in whether an atmospheric river is going to produce hazardous weather. And this is illustrated in this diagram by the two dashed lines. So the lower dashed line here is representing sort of early season drier soils where you would need a lot more precipitation to cause any hazardous weather because the soils are still dry and there will not be as much runoff as it can soak up. So these stronger events are a little bit less likely to produce some of the hazards. In contrast to that, the higher line there would be more of representative of a late season atmospheric river or an area where antecedent soils are already wet and will not take a lot of precipitation to cause significant runoff, and you'll be more likely to have hazardous conditions. Next slide, Jay. So another way to look at the benefit and hazard spectrum of the atmospheric river scale is to investigate the insured flood losses in the Western United States. This was done by a study a couple of years ago from Tom Corringham. And what he found was that about 84% of the $51 billion in flood damages over the US, or the Western US over the last 40 years can be attributed to atmospheric rivers. Moreover, there was an exponential increase in the median damage as the AR rank increased. So from the ARs 1s and 2s showed median damages under about $1 million, but the AR 4s and 5s had median damages in the tens to hundreds of millions of dollars. So this really showed that the scale does a pretty good job in showing the spectrum between the benefits of the lower range ARs 1s and 2s and the significant hazards of the stronger ARs in the 4s and the 5s. Thank you. I'll pass it over to Jay to discuss some of our Ensemble forecast tools. Jay?
Thanks, Brian. So the Ensemble tools are an expansion of the deterministic tools that Brian already mentioned, and you already saw a sneak peek of some of the Ensemble tools with the AR scale. The Ensemble tools are really meant to enhance our situational awareness of landfalling atmospheric rivers, mainly related to the uncertainty, intensity, timing, and duration. We use both a multi-model framework for the ensembles. We have ensembles from the global forecast system. There are 30 ensemble members provided by that system. The ECMWF provides us with a 50-member ensemble, and the West Wharf has a large number of ensembles. Last year, it contained 40 ensemble members, and in the upcoming winter, it will include even more. And so from this ensemble framework and the data that is represented from those ensembles, we can create tools that convey uncertainty and probability and distributions that can help us with situational awareness. We've done this in a number of different frameworks, one of which many people are familiar with is what Marty and I call the AR landfall tool. We also have maps representing the probability of exceedance for integrated vapor transport, getting at the likelihood of AR conditions, as we call it. We also like to show some of the distributions using spaghetti plots thumbnail diagrams, plume diagrams, which are not unlike ensembles of hydrographs, as Brian mentioned, and the AR scale. And we do this using probability over threshold, maps, time series, etc. The first I'll show you is just an example from the AR that made landfall in Central California in January of 2021. These are the 30 GFS ensemble members, or GEFS members as we call them. This is the 7-day forecast from January 20th, verifying on the 27th during our landfalling event. And what you notice is that 7 days in advance of that high impact AR, one of just a few that made landfall in the Central Coast region, there were only about half of the members producing a landfalling AR, with all of the members producing something offshore. So we can use this information in order to come up with a probabilistic answer to, will there be an AR along the West Coast? And you can see there, like ensemble number 23 is pretty robust, where ensemble number 18 is a little bit delayed in timing and a little bit weaker. So from the distribution of the 30 different members, we can create a spaghetti diagram on the left, or a probability diagram on the right. So these are the same forecasts and the same verification times. On the left, what you're looking at is all 30 different contours of IVT of 500 kilograms per meter per second, which is a moderately strong atmospheric river. And what we notice is there's a lot of uncertainty in the location of where the core of that AR is going to be 7 days later. But this should tell us from a situational awareness perspective that there is something in the forecast that we should be paying attention to. And probabilistically speaking, about 50% of the ensemble members had IVT exceeding 500 units just offshore of California. We can combine the probabilistic information into a framework that represents the likelihood of an AR along the entire west coast of the United States, including parts of British Columbia, Vancouver, and down through the Baja of Mexico. So what we're looking at is a slice. Meteorology, we call it a Hofmahler diagram, but you can also think of it as a time latitude diagram, where we're showing the probability of IVT exceeding 250 kilograms per meter per second at each of the dots along the coast. And so if we picked, for example, 38 north here near Bodega Bay, and we go left, the forecast starts here on the right side of the diagram and increases from right to left, intended to sort of show whether or not storms are rolling onshore. And so this starts on January 26th, so just 1 day in advance of our AR event. And we see this like characteristic S shape, which is fairly common for atmospheric rivers that make landfall and then slide along the coast and then stall or produce a mesoscale frontal wave. This shows probabilities exceeding 90% or very high likelihood, at least according to this ensemble. And then perhaps another critter out here 6 to 8 days later in the forecast with slightly lower probabilities extending down into California. This tool has been published in a couple of different articles talking about its utility in forecasting for AR reconnaissance. And Marty and I recently also published a paper providing a verification analysis of this probabilistic forecast. These forecasts are reliable and useful out to 8 to 10 days lead time and can provide effective situational awareness. I mentioned that we use a multi-model ensemble framework. So this is an example of the ECMWF model's depiction of that probability. And if we toggle back and forth between the GFS and the ECMWF, there's a high degree of overlap for the first storm making landfall, and there's uncertainty in the, between the two models in that 6 to 8 day time frame. That shows up really nicely if you stack the images on top of one another, or you could also create a difference field from the two maps, which Chad often shows during our AR reconnaissance activities. The other way is you can pick a point on the west coast of the United States. As Brian alluded to, this is a location-dependent analysis of what the IVT magnitude looks like in an ensemble framework. Each line on this map represents a different ensemble member. The red and blue lines represent the uncertainty in the distribution via the spread or the standard deviation on either side of the mean. The mean is in green, and the control forecast, which is the forecast of the ensemble that they use to then perturb to create all the ensemble members, is in black. And this very nicely shows you the distribution of possibilities associated with IVT, where on January 28th, there's large spread in the timing and intensity of when that AR is going to come on shore. We can also combine all of our ensemble members into a single graphic. This graphic is a Plume diagram that combines the GFS ensemble, the ECMWF ensemble, and our high-resolution West Wharf ensemble members. Each of those ensemble means are represented by different colors. So you can see the orange is West Wharf, the purple is the ECMWF, the green is GFS, and the black is the mean of all of the ensemble members. And the dots represent the maximum values in each ensemble member. So you can identify that the different models have different maxima. The orange dots show up sooner, representing that the high resolution West Wharf suggests a more intense, earlier landfalling AR, where the ECMWF here in purple represents a later, more intense landfalling AR. Again, showing us some of the uncertainty and in timing and intensity. So in summary of both Brian and Mai's presentation here on some of our situational awareness tools related to atmospheric rivers, we construct them from different models, both global and regional, and they provide situational awareness specifically for landfalling atmospheric rivers, but also some of the meteorology behind why we have an atmospheric river in the first place. Our ensembles help us convey confidence and uncertainty, which may aid in decision support applications during AR recon or providing sort of an overview or first look for maybe the decision support in FIRO. We also provide some summative diagnostics, such as the AR scale, the Mediagrams, or the landfall tool, which can give you a good snapshot if you just want a one-stop shop for what's going on in the forecast period. And a lot of these diagnostic tools, the summative diagnostics, have been peer-reviewed and verification statistics exist for these tools.